Hello, Stats class. Here is lesson 10.1c, which, as predicted, is continuing two proportions, but now we're going to do significance tests. So we did the sampling distribution, and then we did confidence intervals. Now we're going to do the four-step tests. And I'd like to just continue the example from the warm-up because it's a good one. So we'll continue talking about hearing loss. And this time, instead of a confidence interval like we did in the warm-up, we'll do a test to see if hearing loss among teens, I guess I'm not going to write all of that, was worse in 2005 compared to 1990. That's the context, as you may remember from the warm-up. And the data that was gathered was a random sample of teens. We actually already checked the conditions, so maybe I can shortcut that part. But the p-hat for 2005 was 0.195 teens with hearing loss, and p-hat for 1990 was 0.15. And the numbers of the samples, we're going to need those, was 1,800. And the number of this sample was 3,000. So that's the data that was given in the original problem. And then we're going to do a hypothesis test or significance test. We're going to do the whole four steps. So here we go. And as we go, I will remind you of what you need to know about the four steps. State. You should be, I hope, getting really good at the four steps. So with confidence intervals, we only had to say our significance level and our parameters. Here we have to do a little bit more because we need our hypotheses. So our null hypothesis, there's two ways to write the null hypothesis. You could either say the null is that they're equal, which some people prefer to do it this way. Notice, by the way, I'm not doing the p-hats, I'm doing the p's because it's the population proportion. I already know about the sample proportions, right? Or you could write it as a difference. So you could write it as P 2005 minus P 1990, or you could have done it the other way. It doesn't matter, and that would be equal to 0. This is usually a 0 if you do it in this form. And I actually don't care which one you choose as long as you're consistent on your alternate, do the same basic style. So on the alternate, we're saying that we think it's more in 2005. We think that teen hearing loss is worse in 2005. And so our alternate is that 2005 is greater than 1990. Or we could write it as the alternate is the difference between those two is greater than 0. For some people, it's easier to figure out the greater than if they write it this way. So I guess that's the big advantage of this way. This emphasizes that our parameter is the difference between two proportions, just like our parameter with the confidence interval is the difference between the proportions. And this emphasizes comparing the two. Whichever one is fine. It doesn't matter which way you write it. And then, of course, we're supposed to also state alpha, which is 0.05. And we're also supposed to say what these represent. So the defining the parameters, some of you are getting lazy about this part. Define the parameters, there's two of them. You have to say that P 2005 represents the proportion of teens with hearing loss in 2005, and P 1990. You don't have to write it all again if you don't want to. You could just put little quote thingies, or you could say same for 1990. But it is really important that you say which is which, especially if you don't use the numbers from the problem. Like if you call them P1 and P2, you absolutely must tell the reader, which is usually me, you need to tell me which one you mean. Because if you have P1 greater than P2 and I don't know which is which, I don't know if you got this alternate right or not. So usually there's a right way and a wrong way to do it, and I need to know if you're thinking the right direction. So the direction is important, and which one is which is important, as well as what does it mean? It means proportion of teens with hearing loss. All right, so that's why we're defining our parameters. That's it for the state step. The plan step has one difference than the confidence interval, but other than that, it's almost the same. So the plan, what we're learning how to do is a significance test. You can abbreviate that. You can leave off the word significance if you want, for a difference of two proportions. And so that's why I was saying this style emphasizes that it's a difference that we're talking about here. The most important words here are test, difference, and proportions. You can abbreviate greatly as long as you have those three things, concepts in there somewhere. The conditions are almost the same as for confidence intervals. So I'm going to teach you one thing that's different, but I'll tell you that the random condition is the same as for the confidence interval. Yes, it was given that they were random samples. The normal condition is going to change a tiny bit, and I'll talk about that last because of that. And I'm going to leave a little space because I want to have room to talk about it, but independent is the same as for confidence intervals, so that won't surprise you at all. Yes, there's three things that have to happen, and one thing is separate random samples. We're not talking about the same teens in both years, or there wouldn't be teens anymore, but we have separate random samples. Or in other words, the samples are independent of each other, and NP and NQ and all of that. Actually, we wouldn't need NP for independent. We would need N 2005 is 1,800, and that's less than 10% of all the teens in 2005. And N, I'm going to put another and because it's important. And 1990 is 3,000, and that's less than 10% of all teens in 1990. So I realize you did that part in the warm-up, but I'm emphasizing that yes, you need the numbers, yes, you need the populations, you also need the separate random samples, so this is complicated, but these two pieces are the same as for confidence intervals. The normal condition is going to change a tiny bit. So we're still doing n times p, and we used, in the confidence interval world, we use n times p hat. But the thing is that, remember when we did single proportion tests, we switched to doing n times p0 instead of n times p hat? We're going to do something kind of like that, except p0 doesn't exist in here anywhere. There is no p0, except that maybe the difference is 0, but what we do instead is we do a thing called pooling, and I'm going to do that down below because I just realized I don't really have room for it here. So I'm going to say pooled proportions is a major thing that changes in both step 2 and step 3. So I'll talk about it here and then I'll come back and finish the normal condition in just a minute. Pooled proportions, or sometimes called combined, is based on the assumption where our null hypothesis is that these two proportions are equal. So we might as well just put all of them into one group. Because we are assuming for our null hypothesis that they're equal, we combine them into one group or pool. And so what we do with that, I'm going to actually put a box around this, I think, because it's so important that I want it to stand out in your notes. The box is not quite ended yet, but we're going to do PC hat. PC stands for combined. I guess we didn't want to call it PP, right? That would be too silly. So anyway, combined or pooled proportion comes from the total number of people with hearing loss over the total of the combined sample size, or both samples put together into one big sample. And that looks like this. It would be x1 plus x2 over n1 plus n2, or in this case, it's the 1990 and the 2005. So I'm going to actually calculate what those x's are with my calculator, because I don't know them at the moment. The 0.195 times the 1800. Whoa, I just typed it really weird. Times 1800. That is my x value for 2005. That's 351. I'll put a little note up here that came from 0.195 times 1800. And then I'm going to do the same thing with the other one. I'm going to do the 0.15 times the 1990. 15% of the teens in 1990. This is the actual number of people. Actually, this isn't very accurate because, you know what? 1990 is not the number I wanted. Silly me. I want the sample size, which is 3,000. Please don't use the year as part of your calculations because it's wrong. So that should have been 3,000. All right, so that's 450. So this is the actual number of teens that had hearing loss in this sample of 3,000. This is the number of teens with hearing loss in the sample of 1,800. And then I want to combine the 1,800 plus the 3,000. And that will give me my pooled proportion. So let's continue showing all the work. We hope that's 801 out of a total of 4,800 teens in both surveys put together, which is 0.167. If they are really equal, then this is my proportion of, this is my theoretical, hypothetical, true proportion of teens with hearing loss. It's my estimate, at least, of that. And then QC hash would be the opposite of that. So it would be 1 minus 0.67, which is 0.833. And these are the pooled values that I'm going to use that come from both samples. So that was a bit of a sidetrack. And now that I have done that, I'm going to use this to calculate the normal condition.